We will start our problem with a quarter circle. Then we're going to connect two corners of this quarter circle, and therefore we will form a triangle inside it. Finally, we're going to pull a parallel line to the bottom radius of the quarter circle, and this line will be divided by our previously constructed line into two segments with the length of 12 and 18, as you can see on the sketch. The question is, can we somehow calculate the red area of this inner triangle? This problem was sent to me by my subscriber Geoffrey from France. So thank you, Geoffrey. And if you guys want to try this one out for yourself, you can pause the video right now and then come back and check the solution. Alright, so let's solve this one. So I'm going to offer you two different methods to solve this problem. The first method will be the classical approach to this problem. And we're going to start this method by first labeling the center of our quarter circle as O. Then I'm going to label two corners of the quarter circle as A and B, and I will also label our parallel line as CD. Finally, let's label the intersection point between two inner lines as E. Now, let's take a look at the radius of our quarter circle and let's label it as R. We can notice that the line OB is also equal to the radius, so we can label it as R as well. Now, since the angle at the point O is 90-degree angle, we can conclude that our triangle AOB is actually an isosceles right triangle. Just as a quick reminder, an isosceles right triangle represents the half of the square. So this means that the acute angle of this triangle must be 45 degrees, since its hypotenuse represents the diagonal of the square. This means that the angle at the point A of our red triangle must be 45-degree angle. Next, let's notice the segment ED. And since this line is parallel to the line AO, this means that the angle at the point D must be 90-degree angle. So, we can use angles in parallel lines. This theorem states that if we construct two parallel lines and pull a line which crosses those two lines, and this line is called a transversal, then we can conclude that each pair of corresponding angles on the same side of the intersecting transversal are equal to each other. So we can use this on our sketch on the left. Since ED is parallel to AO, the line AB is their transversal. So the acute angle at the point A and the angle at the point E are the same, so the angle at the point E must be 45-degree angle. This means that the triangle EDB has two same angles as the triangle AOB, so we can conclude that those two triangles are similar. So this means that the triangle EDB is also an isosceles right triangle. Therefore, the line DB must be equal to 18. Now let's take a look at the segment OD. This segment is nothing but the difference between the radius of our big quarter circle R and the line DB, so it equals to R minus 18. Now, let's clear our image and finally let's rotate the radius OA to the point C. If we do this, you can notice that we will form another triangle CDO, and the angle at the point D equals to 90 degrees, so this means that the angle at the same point on the other side must be 90 degrees as well. And this means that our triangle CDO is actually right-angled triangle. So we can use the Pythagorean theorem. We can say that the hypotenuse OC squared equal to the leg OD squared plus the leg DC squared. And we're going to substitute the values from our sketch. Now we're going to work through this by expanding the first term on the right with square of binomial formula, and we will get the following. Now we can work through this a little bit, and we can cancel r squared on both sides, and finally get that 36r equals to 1224, which means that the radius of our quarter circle equals to 34. Now, remember, we are looking for the area of the triangle AOB, and since this is the right angle triangle, its area will be equal to the product of its legs over 2. In our case, this is r times r over 2, so it is r squared over 2. And we will substitute the value for r and work through this, and finally get that the area of our wanted red triangle equals to 578 squared units, and this is our solution. Now let me show you the second method, which will use a little bit of a different approach, the intersecting chords theorem. So for this method we're going to start with something that we already know. We know that this small green triangle on the top is an isosceles right triangle, so its height must be equal to 18 as well. We have proven this in our previous method, so we're not going to do that all over again. Now, with this knowledge, we're first going to erase the hypotenuse of our triangle, and we're going to say that our parallel line equals to 12 plus 18, which equals 30. Now let's shrink this sketch a little bit. Then let's label the center of our quarter circle as O and its radius as R. And let's make a full circle. Now let's extend our line with the length of 30 to the other side, and in this way we will form a chord to this circle, which we can label as AB. Of course, we're also going to extend our vertical radius downward, and we're going to get another chord, which is also the diameter of our circle, and let's label it as CD. Finally, let's label the intersection point between our two chords as P. Now, since the line CD represents the diameter of our circle, this means that the line PB must be equal in length as the line AP. And since CD is the diameter of the circle with the radius R, this means that the line CD must be equal to 2R. And since CP equals to 18, this means that the segment PD must be equal to 2R minus 18. Alright, so let's clear our sketch a little bit. And as you can see, now we have two intersecting chords, and we're going to use the intersecting chords theorem. This theorem states when two chords intersect inside a circle, then the product of the lengths of the segments of one chord equals to the product of the lengths of the segments of the other chord. As you can see that I have labeled the sketch on the right the same as sketch on the left. So we can use this theorem in our case. We're just going to substitute the values of our segments from the sketch, and we will get the following. We're now going to expand by multiplying, and we will get that 36r equals to 1224, which means that we got the radius of 34 of our circle as we did before. Now let's go back to our previous sketch, and remember, we are again looking for the area of our red triangle, which is actually an isosceles right triangle, so the area will be equal to the product of its legs over 2, or r squared over 2. Again, we will substitute the value of r and work through this, and again get that the area of the red triangle equals to 578 squared units, and this is our solution. Well, I really hope you guys enjoyed this video. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. And of course, if you found another way to solve this problem, write it down in the comment section. And until next time, see you guys and take care.